Hey, how you doing? I'm Elton, and this is part 3 of Modernizing .NET Apps for Developers, a series showing you how to take existing .NET Framework apps, run them in containers, and use the Docker platform to modernize the application architecture. In part 1 and part 2, I got my Web Forms app and my SQL Server database running in containers, and I integrated my application configuration and logging with the Docker platform, all with no code changes. In this video, I'm going to start breaking down the monolith. I'm not going for a full microservice re-architecture. For a real-world app, that could be a 12-month or 18-month project. Instead, I'm going to drive this modernization by features, so each incremental release is fast and brings tangible benefits. So here we go. This is the current architecture of the application. I have containers for the web app and for SQL Server. When a user submits the sign-up form on the website, the app inserts their data into SQL Server. That's a synchronous database call, which makes it difficult for me to scale my app. I can easily run hundreds of web containers to handle the incoming load, but if they all try to make database calls at the same time, they'll starve the SQL Server connection pool and users will see errors. So in this video, I'm going to break out the save feature and run it in a separate container. This will be a .NET Framework console app, which listens for events being published to a message queue, and the queue is also running in a container. I'll change the web app, so when users fill in the form, the app publishes an event to the queue, which the new console app will pick up and action. This is an asynchronous workflow, which decouples the web app from the database. I can scale up and run many web containers if there's lots of incoming traffic. The message queue stores events until the handler actions them, so it smooths out any peaks without overloading the database. This isn't a big code change. I need to change the web app to publish an event to the queue when a user signs up, and I need to move the save logic into a new console app which listens for events and then saves the data. Let's see how that looks. The first thing I've done is physically broken down the code base. Originally all my code was in a single web project, but now I want to share the Entity Framework model, so I've extracted that into a separate project. This is still version 1 of Entity Framework, because I don't want to bring an EF upgrade into scope. That could be a lot of work, and here I'm just focusing on one performance issue. I have updated the .NET Target Framework to 4.7.1, which I've done for all the projects, so I can use new features, and when I add new dependencies, I can use the latest NuGet packages. I also have a new entities project, which has plain object versions of the classes in the model. I don't want to publish Entity Framework objects in my events, because that means any consumers have to also take a dependency on EF. And I have a messaging project which wraps up the logic for publishing events in the message queue class, and it also contains the event message classes. The prospect signed up event is going to be published from the web app. It contains a prospect entity and sign up date, which is everything I need to save the data, and it has a message type, so subscribers can filter on this type of event. Now, in the web application, where I used to save the new prospect directly to the database, I now create an event object, populating the prospect entity from the model object using AutoMapper, and I publish that to the queue. Apart from the restructuring, which makes for a cleaner and easier to test codebase anyway, this is a pretty small change. The save logic has been moved into a new console project. The console app starts by setting up AutoMapper for the model to entity mappings. Then it uses the same message queue class to connect to the queue and subscribe to prospect signed up events. When it receives an event, it calls the save prospect method, which uses AutoMapper to build the Entity Framework object and then saves it to the context, using the same code that was originally in the web application. I'll be running the console app in a container, and I've updated how the web app gets packaged, so I'll walk you through the Docker files. The Docker file for the message handler uses the same pattern as the web app. I start with the builder stage, which works from Microsoft's .NET Framework build image. That image has NuGet and MS Build and .NET 4.7.1 installed. So in the first stage, I run NuGet Restore for the console app and then run MS Build. The final stage starts from Microsoft's .NET Framework image. This has .NET 4.7.1 installed, but none of the build tools, so it's the slimmest image I can use for a .NET app. I'm using environment variables to configure the path where the app gets deployed, and the URL of the message queue, which will be in a container called message queue. I'm also using the same configuration pattern from the last video. There's a path to the database connection string config file. In the app config, I'm pointing to a default config file, and the default setting will connect to a database container called signup.db. The console app gets started in the container from this PowerShell script, which sets up the config file using the same symbolic link pattern, and then runs the exe. The Docker file for the web app has had a few changes. I'm using the 4.7.1 build image and the 4.7.1 ASP.NET image. I'm also capturing the message queue URL in an environment variable, and the rest is all the same. For my app to run now, I need some more components, and these are all defined in the compose file. I have the database and version 3 of the web application, and I also have the save handler console app and a message queue. The message queue I'm using is NATS, which is a high-performance open source queue that has public images on Docker Hub. I don't need to build my own image for this, I'm using the image maintained by the NATS team. I have a second compose file here too. Docker Compose can merge together multiple files, and this is an override file that contains the build details for my own images, the path to the source and the Docker file. I can build the whole application through Docker Compose by specifying the original file and the new build override file. The build command uses the Docker API to build each image, which in my case is going to compile the applications and package them too. While that's running, I'll show you how you can use Docker Compose to make your CI/CD pipeline super easy. I'm running Jenkins as my automation server, and I have jobs here to build each branch of the code. This is part 3, and the configuration of the job is really simple. I have some bindings which let me use secure information in the job, and I'm using certificates to connect to my Docker server. In the build steps, I just have simple PowerShell scripts. They all look the same. I set up a config object with the details to connect to the Docker API, using the server IP address and the certificates, and then call a script which is from source control. The build script just runs the same Docker Compose command to build the whole app. When this runs in Jenkins, the config object has been populated, so the images will build on the remote Docker server. When I run it locally with no config object, it still runs, but it will use the local Docker API, so developers can use the exact same scripts as the CI server. The next step in the job starts up the application using Docker Compose, then it lists all the running containers and sends a request to the web application to warm up the website. The test step runs a suite of spec flow tests inside a container. I won't go into detail here, but you can see in the source code how that's all set up. And lastly, everything gets stopped using Docker Compose down. Because all the build steps run with the command line, the output all gets captured. Here in Jenkins, I can see the images being built, the test being run, the container lists, and the final outcome. Oh, and this Jenkins server is actually running in a Docker container too. As the app gets more complex with more containers running, the build scripts don't need to change. These are just wrappers for Docker Compose where the whole application is defined, and I use those same compose files to build, run, and test the app. I'll execute the run script here, which starts all the containers, and I'll browse to the container's IP address, which I get in the output. The app is going to look the same, and it has the same reference data populated from the SQL Server container. Now I'll add some data to the sign-up form and submit it. The behavior is the same from the user's point of view, but now the save happens asynchronously. I can look at the running containers and check the logs of the save handler. This shows it's listening for event messages, it's received one, and it's created the details in SQL Server. The ID field comes back from the database, so we know the save has been successful. So now my legacy .NET 3.5 app is running in the latest version of .NET in Docker containers, and I've implemented event-driven architecture for one of the key features. In that demo, I've shown you how you can start breaking up monolithic apps. I've taken a synchronous feature out of the web application, moved the logic to a console app running in a separate container, and used event publishing to integrate them together. The message queue I'm using is NATS, and now my traditional app is running in a distributed architecture. There are some serious benefits to this. I've fixed the scale issue. Now I can scale the web app and the message handlers independently, and a spike in traffic isn't going to max out the database. I've also taken a key feature out of the original codebase, and now I have smaller components which are faster to test and quicker to deploy. They can be deployed independently too. If I want to add audit details to the save, I could roll out a new version of the message handler without any changes to the running web application. Modernizing the application architecture is an enabler for further development too. I have a proven pattern now for running back-end features in small units and integrating them with a message queue. I can do the same to break out more features from the app, or I can add new features. Using Docker made it really easy to adopt new architectures in my monolithic app without having to do a full rebuild. In part 4, I'll make use of event publishing to add new features, but I'll finish up this time with a look at how the new version runs in production. I've deployed my application as a stack in Universal Control Plane. There are services running the web application, save handler, and message queue containers. I'm still using SQL Azure for the database, so the save handler is configured with a secret to set up the database connection string. It's the same secret I use in the web app, so I've got my environment configuration centralized and secure. My UCP cluster has several nodes, so I can run my application at scale. I have 3 instances of the web application container and 4 of the save handler. That gives me high availability and failover. If one of my containers fails, Docker spins up a replacement. If one of the cluster nodes goes down, Docker starts replacement containers on other nodes. Again, the UX of the app hasn't changed, so I browse to the Azure load balancer and I see the same site. This page could be served from any of the web containers. I'll add some more details to the sign up page and submit it, which publishes the event message. Now, any one of the handler containers will pick up that message and save the data. I can check the logs to see the data has been saved. I've got my ID back from the database, so this is all looking good. That's it for part 3. I've started to modernize my application by breaking down the monolithic codebase into separate components and integrating them with a message queue. That fixes a specific performance problem, and it lets me scale my app by running multiple containers in a clustered environment. It also gives me an easy way to extend my application, adding new features without having to change existing components. The event-driven architecture I introduced means I can add new functionality by adding more message handlers, and that's what I'll do in part 4, adding analytics to the application using more open source software running in Docker containers. That's coming next, in part 4 of Modernizing .NET Apps for developers. If you want to get started modernizing your own apps with Docker, head to the Play with Docker training site, which is an online environment with Docker configured that has lots of great tutorials. And if you want us at Docker to help you modernize your application suite, head to docker.com/MTA to learn how we partner Docker architects with infrastructure providers like Microsoft and consultancies like Accenture to bring your apps into the modern world.